Now, we were talking about the car, and when the car goes faster, we get more force slowing it down. Do you remember that? What's this one called? The drive. And then this one here is called the force at the back here is called the drag. And when they're equal, constant speed. Right. If we look at the graph for the car, it starts at velocity and time. It starts off at rest, then it gets faster, 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 but it doesn't keep getting faster. What happens? It reaches a constant speed, like we said. This constant speed has a special name. Does anybody know its name? This speed here, the maximum speed. Oh, very good. Terminal velocity. Terminal velocity. That's what that's called. What's the maximum velocity? Okay, so we continue that idea here. Next. Can I go down? Yeah. Now, let's see here. We have this mass here, and it falls. What's its force? It's W, which is mg. Yes? And what's Newton's second law? F equals ma. So if I put these together, you get ma equals mg. So then what does A equal? G, which is 9.81. Now that's very interesting. It means that when something falls, its acceleration is always 9.81. Notice how it doesn't matter about the m. It's always 9.81 when it falls. So, if I have something really, really heavy and really, really light, they fall together, right? But why, if I drop a hammer and if I drop a feather, why does the hammer fall faster than the feather? Not so much the mass, no. Because we see here that the mass is not important. And the reason is, when it's falling, we shouldn't forget there's actually a drag going up. And this drag here is going to depend on the mass, the shape, the size, all these different things. So when you drop a feather and a hammer, the feather goes slower because the air is slowing it down. But what if there was no air? Do you think they follow the same? Yeah. So, video time now. Okay. Oh yes. Yes, yes. Video time. So we're going to see a video of a feather and a hammer falling, but with no air. So they should fall together, if I can find it. Did I put in physics? Do I even have a physics? No. Physics. Yes. Right, I better pause this recording. So we continue. So now, the next thing we're doing is the most important idea in physics. Most important idea in physics. So what is so important? Well, don't look at your page. Does anyone know what I'm talking about? The most important idea in physics? No? I'll tell you now. So this is the name of the lesson. You know what I'm talking about? Anyways, we'll talk a bit about energy. So what is energy?
Calories.
Yes, it's related to calories and joules and so on, yes? you're right. So, does anyone want to try and give it to me as a sentence? Energy is... Yes. The ability to do work. So, here's our person. And this person eats 7 polos, right? So they have polos here in their stomach, and this person here has no food. So this person can do work and this person can't. So we say that this person has energy and this person does not, because this one can do work and this one can't do work. So if you can do work, you have energy. So that's the first thing. And when you think about it, everything has energy really, because everything can do work. For example, I can do work, the lights can do work, everything can do work. Okay, so what we have now is there are many forms of energy. So food has energy in it, because you can eat food and this can let you do work. Right? So there's many forms of energy, and we're going to look at 2 special forms today. So the first one is called kinetic. We'll do first. Kinetic energy, or KE for short. When a mass is moving, when a mass m is moving with speed v, we say it has kinetic energy. So I'll give you an example now, try and show you somehow. I know. Maybe. So remember when I said work is force by distance. So if I push this, then I'm doing work, okay? But of course, I could hit it with something. Now, if this is going faster, will this move more? Yes. So if this is going faster, it can do more work. And what about if it's bigger? So if I replace it with something else, bigger mass. Oops, too much work. Thank you. It can do more work, right? So the amount of work this can do is called the kinetic energy. And there's a simple formula to work out how many joules of work you can do. And I'm sure people know this, some people know this. The kinetic energy is a half v squared. You've seen this before. You have it. So if we make the mass bigger, or we make the speed faster, we can do more work from it. Can you picture a waterfall, and the water comes along and goes down, and it's going really fast, and then it hits a wheel, and it turns the wheel, and we use this to make the bread. You know? I don't know if you have it in your home country. You know what I'm talking about? Yeah, in the windmills, like for the flour, for the bread. So the water comes along, the water goes down, and then the water turns a big wheel, and then this big wheel turns a big stone, and it makes the flour for the bread. Crushes it, yeah. So there's a force, isn't there? The stone is turning. There's a force here. Where did the energy come from? It came from the water that was moving the big wheel. Okay? So again, I'm just saying, if it moves faster, it can do more work. Okay? Now, I said there are 2 types we'll look at today. So that's the first one. And yes, well, some people already know the next one. There's not going to be a surprise for them. Potential. Oh, that's not spelled right. Arms are tired. Okay. Potential energy. PE. When a mass m is h meters or h high, we say it has potential energy. And the very, very important condition here is near the Earth's surface. Okay. So if we think here for a moment, oh well, I'll write it down. So if I hold this here, and I drop it, it hits my hand, and you know, that's a force that can do some work. If I hold it higher, can I do more work? Yeah, because what happens is it hits my hand, oh dear, too much work again. I'm just going to get in more trouble now. What's this for? Oh yeah. Hopefully it won't break. So if I hold this higher, I can do more. Okay? But what about if this is bigger mass? Do more as well, yeah? So potential energy, if it's big mass and it's very high, there's lots of energy in that. Okay? So we have this formula for potential energy. mgh. Now, I said there are many forms of energy. This is only two of them. Do you think you can give me more forms? Think. So what I want you to do is think about all the ways you can have energy. So I said one is food. Food has energy. Because you eat it, you can do work. And we have kinetic and we have potential. What else is there? Well, yeah, chemicals like the food, yeah. There's electrical energy. Solar, light energy. And then of course, heat energy. What else? Wind energy, yeah. Many different types of energy, and they all have different formulas. Here's the two basic ones for us, kinetic and potential. Okay. So, let's see. Does anybody know their mass exactly? And it's not shy about sharing it. I know you know your mass, don't you? 51, right. So, let's say he eats 7 polos. Let's see how fast he can run if he eats the 7 polos, okay? So how much energy did we say were in the 7 polos? 4.2 times, no, what was it? 42 times 4.2, wasn't it?
Yeah, it was 176.
176.4. So, this is Abraham, right? He eats the 7 polos, so he gets 176.4 joules of energy. And he uses this energy to run. So, what he is doing is changing this energy into kinetic energy. What's the formula for kinetic energy? A half mv squared. So we have a half mv squared equals 176.4. What did you say the m was? 51. So a half of 51 is 25.5. V squared equals 176.4. So divide square root. What's that? It's not too big.
2.6.
2.6. That's not a lot, but it's only 7 polos, okay? So 7 polos, you know, that's enough energy to get you going at 2.6 meters per second, okay? But this is what I'm trying to get you thinking about. The next idea is that, and this is what I mean is the most important idea. The name of this lesson is conservation of energy. Conservation of energy. What does that mean? Well, let me write it down here. And my goodness, this is very important. Conservation of energy. Energy cannot be created or destroyed. It only can change form. So what does that mean? I'll explain it now once you write that down. Okay. I'm not joking when I say this is the most important idea in physics. It's the most important idea. You cannot make energy. And I'll say that again. You cannot make energy. And you might say, well, Mr. Stephen, can't you? And I'll say, no, you can't. You can't make energy. So let's take the example with Abraham again. When he's running, what type of energy does he have when he's running? Kinetic energy. Where did he get that energy from? From eating the polos. Okay, let's not use polos because that's kind of weird. Let's pick something like, what's your favourite meat? You eat meat, right? What's your favourite meat? Lamb, chicken, fish? Chicken's good? Alright. So he's from kinetic energy, and he got that from the chicken he had for lunch. Okay? So, where did the chicken get the energy from? The feed. The chicken at the chicken feed. Where did the chicken feed get energy from? From the seeds, yeah, okay. Where did the seeds get their energy from?
From the solar energy.
From the sun. You see? Where did the sun get that? You see, you keep going back. You can't make energy. It always comes from something else. Okay? So like, for example, the light energy. Well, where did the light energy come from? Came from the electricity. Where did the electricity energy come from? It came from the power plant. Where did the power plant energy come from? How do you make energy in a power plant? What do they do? I'll keep it more simple though, like you burn something, yeah? Coal. Well, what is coal? What's coal? Coal, oil, gas, what are they? Fossils. What are fossils? You know what fossils are?
Yeah.
What are they? Fossil. Coal, oil, gas are fossil fuels. What are fossil fuels? They're dead animals, aren't they? That's what they are. Where do the animals get their energy from? From the food, and the food from the plants, and the plants from the sun. You see? So, yes, circles like physics style. So, all energy comes from a source. You cannot make it. It's the most important idea in physics. And it's very useful. It lets us solve many problems. So we'll have a look at some of the examples now, okay? Most important. Did you all write that down? Yeah, okay. So let's have a look at some examples. So for example, here we have, for example, I don't know. No, here we have like a ball. And here is 10 meters. So at the top, this ball has energy. And when it falls down here, it still has energy. At the top, this ball is not moving. What type of energy does it have? It has potential energy. On the ground, the ball has no potential energy because it's on the ground. What type of energy does it have? It has kinetic energy. The energy does not change, so that means the potential energy at the top must still equal the kinetic energy at the bottom. So how much potential energy does it have at the top? Potential energy at the top. Let's work it out. The energy at the top equals the potential energy, which is mgh, oh yeah, let's say it's 10. So that's 10 by 9.81 by 10, which is 981 joules. When it hits the ground at the bottom, it has kinetic energy. What's the formula? A half mv squared. And that must equal 981. It doesn't change. So a half m, that's 5v squared equals 981. So, do a little bit of simplifying. What do I get there, please? 14.007, so 14 meters per second. Okay, now I'll go, sorry, can I go on? Yep, okay. So let's look at another example here. Okay. So I have this ball, 10 meters, well, maybe it's not a ball because it's 10 kilograms. And the ball goes, it falls down and goes dunk, 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 dunk. How fast is the ball going? Now before the lesson today, you might say, that is way too difficult because you have this sort of UVATS projectile problem, and then projectile, 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 projectile. But we can use our conservation of energy. The energy here, E1, must equal the energy here. Yes? What energy does it have here? Does it have any kinetic energy? No. It just has potential. And what about down here? Yeah, does it have any potential? No, it just has kinetic. But if you stop, you realize my numbers are the same, aren't they? 10 and 10. What was it in the last example? 10 and 10, wasn't it? So in fact the answer is the same. Now this is really useful. It means you don't need to worry about the past. You only need to care about the start and the end. You don't care about the journey. So that's very, very useful. So let's have a look at a real example now. Okay. Actually, no, I'll give you one to try. If I go down here. Okay, so here. We have our ball on the ground, and I throw it at 15 meters per second. Yep. Now, when we did our projectiles lesson, do you remember how to find the highest point? What did you have to do? Vy in the y equals 0. Remember that? But you can use energy now to find this. What type of energy does it have at the start? Kinetic. Oh, well, there's a problem here. It's kinetic and potential. Yes, okay, sorry. I'll keep the same, but let me just give you more information. So here we'll say this is 9, and this one here is 12 as the 2. Okay, so here we have kinetic. What type of energy does it have here? It has kinetic and potential because it's moving still. It hasn't stopped in the air, it's still moving. So what I would like to do is find the height here. I think I've made this too difficult. I have. No, I haven't. We can still do it. So, let's do, no, don't remove that. No, too much. What did I say was here? 12, okay. Right. Energy here, kinetic plus potential, and then here, it's only kinetic because it's on the ground. And the mass, what did I say it was? What did I not say? 5. Was I? Okay, let's get the energy at the start. It is a half v squared, which is a half 5, 15 squared. What's that, please? 562.5 joules. The energy at the end is a half mv squared plus mgh. But the energy at the start, oh, V's not 0. No. This is why I was worried it was too difficult. But no, we can still do it. The energy at the start must equal the energy at the end. It does not change. We have 562.5 joules. Okay, what's the m? Was 5, wasn't it? So that's 5 over 2 v squared plus 5 times 9.81 times h. Can you just tell me this number here, please? Joules. Well, I won't write the joules for the moment. 2.5 v squared plus, what's this? 49.05. Now, the reason, Ugo, that the v is not 0 is because the v in the y is 0, but the v in the x is not 0. Now, when you look at the ball, look here, at the start this is 9 and 12. Here, this is 9, and then this is 0 here. So the speed is 9. Or if you want from Pythagoras, it's square root 9 squared plus 0 squared. And here the 15 was square root 9 squared plus 12 squared. Anyway, the speed here we can see is 9, because this one doesn't change. Remember, the horizontal stays the same. The vertical changes. So that means I know that this is 9. So I have 565.2 equals 2.5 times 81 plus 49.05 h. So 5625 minus 2.5 times 81 all over 49.05. What's that, please? 7.33? Yeah. Yes. Now, what I'm going to do for fun is I'm going to do this but using the projectiles. Yes. Oh, sorry, you need a minute. So I'm going to do this again but using projectiles. The UVATS. Okay. So the second way to do it. Great. So we have UVATS. So if I go back here, vertically, what's the U? It's 12. Yes? What's the V? This is in the Y. 0. What's the A? Minus 9.81. And the S? We don't know. That's what we want. So we have V equals U plus AT, so what's the T? You know what, I don't even need to do that. I can just use V squared equals U squared plus 2AF. 0 equals 144 minus 9.81 as well. 2 times 9.81 times F, so then F equals 144 over 2 times 9.81. What's that, please? Oh, I'll just check it for kicks.
Okay, 7.3.
You did check it?
Yes.
Because I could have made a mistake?
No, I checked.
Alright, 7.34 meters. See? Same answer. Same answer. Okay. Another example now, and this is one I'll have you try. Can I scroll down? Yeah, okay. So here, here, we'll put Abraham on the swing, will we? Yes? So what we have now is here, let's say this is, oh, I don't know, 1 meter. And then what happens is he swings down, and then he's down here. 0.1 meters off the ground. Oh yeah, what was mass? Is 51 kilograms. So my question is, how fast is he going here? So the energy at the start, what type of energy here at the start? It's potential. Is there any kinetic? No, because it's at rest here, okay? So potential at the start equals, what type of energy does he have here? Kinetic and potential. Kinetic energy at the end plus potential energy at the end. So now, I would like people here to give me the speed at the end. Okay? And then I'll do it in a moment. So tell me what the V is at the end. Does anyone have it yet? Nearly? Yeah?
I got 4.2.
Okay, let's do this one now. So, the potential energy at the start is mgh. The kinetic energy is a half mv squared, and the potential energy is mgh, but this height is different to this height. It changes height. M, 51, G 9.81, H 1, a half 51 V squared plus 51, 9.81 and 0.1. And when you solve this, you get V equals 4.2. Okay. Now let's link this into the previous lesson. Can I move? Yep. So I want to go right back to the start if I can find it. The example with the box. Here. Here. Yeah, here. So, yes, we got originally 196.2 joules. And how big was the box? 10 kilograms, and the height, 2 meters. Right, so, let's look at this again, but with energy. So the box here is on the ground. What did I say was 10 kilograms. Later, the box is up higher, 2 meters higher, yes? Still 10 kilograms. The energy here, does this have kinetic energy? Is it moving? No. Does it have potential energy? No. So how much energy does it have? 0. It's at rest on the ground. No energy. Is this moving? No. So does it have kinetic energy? No. Does it have potential energy? Yes. mgh. So the m is 10, the h is 2, and the g is 9.81. So if I work that out, 2 times 10 times 9.81, what do you get? 196.2? Yes? Is that right? Calculators?
Yeah.
100 and... Now we have a problem. I just said the energy is the same. How much energy here? 0. How much energy here? 196.2. This is impossible. But not impossible, because the energy came from the man. So this man here at the start, and the man at the end, I'll draw him over here, he had 196 joules of energy, and at the end, he no longer has this energy. He has given this energy to the box. So, in total at the start is 196 plus 0. In total at the end, it is 0 plus 196. So, this man, he did 196.2 joules of work. He gave it to the box. And you see, that's the same answer when you use this formula. Okay? So you see, I'm trying to link the two together. It's a lot. So we can also say, you know, if there's a change in the energy, it's no longer constant. That's because somebody or someone gave it from them. And this is another way to think about work, is the change of energy. You know? So here, let's see, I put this here. This has no energy. This has what type of energy? Potential. It got it from me. So now I'm a little hungrier because I did that. Yes? Okay, I'll get you a small one. There's a small question to do here. So this box, how much energy to lift this, what was it, 10 kilograms? It was 10 kilograms and 2 meters. How big is 2 meters? About here? Okay. That's 196 joules. So it would take about 200 joules. You bend down, you pick up the box, and you put it on the shelf. And then you do it again. How many times must you do this so that you burn all your calories from the day? So how many calories do you need a day? 5 minutes, 2,000, isn't it?
2,000.
2,000 kilocalories. So type it in 2,000, multiply 1,000. Yeah? Now, how many joules in a calorie? So multiply 4.2. So how much joules of energy do you have in you when you eat all your food for the day? It's a lot, isn't it? How much?
8.4 million.
8.4 million joules of energy in your body when you eat all the food. Divide by 200. 42,000. So you have to do this 42,000 times so that all the energy from all the food you ate is gone for the day. So, do more work or eat less? Eat less, right? 42,000. Now, it'll be less than 42,000 because when you lift it, you also are doing other work too, like, your body is warm, you're also moving your feet on the ground. So it's actually not 42,000, maybe it's 10,000. But it's still a lot. Okay? Right. I'll let you try these now. Oh, you have the page already. So we go to the next page. Yeah, okay. So I'd like you to do these questions now, and I think all of them will be of exam difficulty. Yeah. So you should be able to do all of these, and you can start them now. Well, do you have time to finish them? Oh yeah, you might get them finished now before you go home, okay? So you can start this page now.